Today we continue our factoring journey by talking about special cases for factoring. These are ones you've probably seen previously as we've been working with quadratics up to this point. They're also on the star chart as the first 3 rows on the star chart. So there's 2 special cases that we're going to talk about. The first one is called a difference of squares, or sometimes called a difference of 2 squares, depending on where you see it written. And it's basically the idea of when we did the area model and we had no x's in the final product. So we had something like x plus 7 times x minus 7, and it gave us x squared minus 7x plus 7x minus 49, so that when we combine these like terms, we end up with x squared minus 49. And you probably also at this point recognize that that means there's no horizontal translation on that parabola. So if we were to graph it, it would lie somewhere along to where the vertex is on the y-axis. It may have moved up or down. In this case, it moved down by 49 units from the parent function, but it has not moved left or right because there's no b term in the standard form. Also, you could think of it in vertex form. This is x minus 0 squared, so our horizontal shift was 0. So this is the case we're talking about, and it's called a difference of squares because once you put it together, this x squared minus 49 is 2 perfect square numbers. X squared is a perfect square of x times x, and negative 49 is a perfect square of 7 times 7. This only works if we have a difference of squares. So this symbol in the middle has to be a negative symbol. If it's a positive, we can't do anything with it. So our notes for today are going to lead us through how to recognize and use this special case to shortcut the process of factoring. So this is basically a handy shortcut for how we can see this square minus square and then jump straight to this instead of having to worry about doing something more complex. But just like every method of factoring, we always look for a GCF before anything else. So the first thing we do when we're trying to factor is look for a greatest common factor among all the terms. After that, we're going to look for numbers that are perfect squares. So perfect squares, hopefully we know them at least through 15 or 20, are like 1, 4, 9, 16, 25, and so on. We're going to use I actually don't know what goes here. Let's just put difference of squares pattern. Difference of squares pattern to factor the expression. The idea is we're factoring it like this: a plus b times a minus b. So, as an example, we have 4x squared minus 9. There's no GCF, so we can move on beyond that and look at the fact that 4x squared is a perfect square of 2x times 2x. 9 is a perfect square of 3 times 3. Since there's a minus in the middle, then we can write this as 2x minus 3 times 2x plus 3. I don't know why I wrote the minus first. It doesn't matter. The order you do it doesn't make a difference. Usually we write the plus first, though. So we had 2 important things. So we saw that we had a perfect square and a perfect square, and they must have a minus in between. So if I put 4x squared plus 9, even though these are both perfect squares, I cannot factor this as a difference of squares. Difference is a really important keyword. It means subtraction. The second one we have here does have a GCF. So before we try to look for a difference of squares, we write 2 and then it has 2d squared, sorry. So 2d squared is our GCF, and then we're left with d squared minus 36. So now we look at d squared minus 36. This is a perfect square of d times d, and 36 is 6 times 6. So this can become 2d squared is the GCF. Then we have d plus 6 and d minus 6 is our difference of squares factored out. So that's that pattern, and that's really all you're doing is looking for two terms with a minus in between that are both perfect squares after you GCF it. Yeah, that's it. And you'll never ever look for this if there's three terms, right? If you have a trinomial, it cannot be a difference of squares. It is two terms with a minus. All right, that's how we look. We always look for it if we have two terms that are a difference. This other one is a pattern we look for when there are three terms, and it's called a perfect square trinomial. We've actually encountered these and worked with them quite a bit when we converted vertex form into standard form, for example. So if we had y equals, and then we had x minus 1 squared, say plus 2, then when we converted this to standard, we had to multiply x minus 1 times itself. And we could do that using distribution or the area model, or some of you have already been using this shortcut. But if not, this is the time when we want to start recognizing it, because it's going to allow us to undo the work of multiplying it out. So x squared minus x and plus 1. So x minus 1 squared leads us to x squared minus 2x plus 1. And the pattern is what it shows here. Something plus something squared gives you the square of the first thing plus 2 times the product of the two things. So that would be this 2ab is coming from these two boxes, which will always be the same if we're squaring a binomial. So we get minus x and minus x, which is x times negative 1, and then we double it because there's two boxes that have that value in them. And then the last box is b squared, because that's like the lower right one. So let's color code these real quick. So a squared is coming from here. That was x times x. And then we saw where 2ab came from. And then b squared is coming from this box, which was negative 1 times negative 1. So if you're having trouble visualizing where those come from, hopefully that will help you to see that. There's two versions of this. There's only one written here, but the difference is just this symbol in the middle. So this is a perfect square of a binomial with a plus. So that's a plus b squared is equal to a squared plus 2ab plus b squared. But notice that in the one that we did as an example, we had a x minus 1 squared. So we ended up with a negative 2x in the middle. The third term is always positive, because it doesn't matter if b is positive or negative. When we square it, it becomes positive. So you can just use this one version, but just remember that when you do this part here, 2 times a times b, you take the sign into account as well. So for the example that I wrote, that would be 2 times x times negative 1. So our middle term would become negative 2x. Usually there's two different versions written out like there are on the star chart. It has a plus b squared separate from a minus b squared, where this one is a squared minus 2ab plus b squared. Because again, the last part will always be positive no matter what, and we saw that with this pink box in my example. So the difference between the two is this plus creates this plus, and this minus creates this minus. Okay, so let's see if we can guess what goes in the blank. Well, we know that step 1, no matter what, is always look for a GCF first. That's always the first step of any factoring process. Next, we're going to look at the A and the C term, which are the first and the last term, or the x squared and the constant term. There's a lot of things that could go in that box. I think I'm actually settling on, instead of a and c because that's more abstract, let's say look at the x squared and the constant term. So the thing we start and end with. Are they both perfect squares? So we're recognizing the same kind of numbers that we did with difference of squares. 1, 4, 9, 16, 25, all of those magical perfect square numbers. If yes, so that's the first check. If not, we can't consider this as an option and we just move on from it, and we can't factor it as a special case. If the first and last terms are perfect squares, then we have to check, does the x term, the middle term, so we can still put first, last, and here we can put middle, does it equal 2 times, shouldn't use x because we already have a meaning for x, 2 times, I came up with a better word. Let's put double. That means 2 times, and it's a single word. Does it double the first term, equal double the first term, multiplied by the third term? Not quite right. Does it equal double the square root of the first term multiplied by the square root of the first times square root of the third? If yes, use the perfect square trinomial pattern to factor the expression. So if that third step was a little unclear, we'll just see it in some examples here. So number 1, we look for a GCF. There is no GCF. So we move on and we say this is a perfect square of x times x. This is a perfect square of 6 times 6. Then we check, is the one in the middle double this times this? So we're not looking at the x squared and the 36. We're looking at these square root factors. So we say, is negative 12 equal to negative 12x equal to 2 times x times 6, and it is. So we're not worrying about the negative because remember that just changes the sign here in our factored version. What we really care about is the number part. So we're going to write this as x and then 6. I'm going to fill this in, x and 6 and x and 6. And then to decide on the symbol in the middle, we're looking at this symbol between the x squared and the x term tells us what goes here. So we end up with x minus 6 times x minus 6, and we actually are going to just simplify that into, or group it together into x minus 6 squared. Now, you won't write all of these steps, right? The idea of a shortcut is that we see this pattern and we just go straight to this. We don't have to write all the stuff in the middle. I'm just explaining the thought process because it's new and we're just getting used to working with it. So I'm going into way more work and detail than we actually would want to do here. The next one has a GCF of 3. So we'll factor that out first. We have 3 times x squared minus 10x plus 25. My first term is a perfect square, x times x. My last term is a perfect square, 5 times 5. So I check, is the middle part double x times 5? Well, that's 5x times 2 is 10x, so yes, it is a perfect square trinomial. I write my perfect square as x. I check my sign right here and put minus 5 squared. So that's more along the lines of how fast we want this to be. We don't want to write out a bunch of steps. All right, in each of these, we're looking for special cases to factor these. And it's a really easy check first. We say, how many terms are there? If there's 2 terms, we're looking for a difference of squares. So 2 terms is difference of squares. 3 terms, we're looking for a perfect square trinomial. There are no cases where it could be confused between the two, right? Difference of squares only works when there's just 2 terms. Perfect square trinomial has to have 3 terms. So this first one, this is x times x and 3 times 3. And it's a 2-term thing, so it's a difference of squares. So we're going to identify on each one what it is, and then I'll come back and write out what they factor into. This one is 2y times 2y and 5 times 5. This is a difference of squares, and I am paying very close attention to the sign, right? This is a minus sign and a minus sign. If there's a plus sign, it is not a difference of squares. The next one, this is 4a times 4a, 9 times 9, there's a minus in the middle, so this is a difference of squares. Next one is, and I'm checking for GCF as well, I'm just not saying it if there's not one. This one is 7m times 7m, we have a minus, 2n times 2n, this one is a difference of squares. Next one, this is 10p times 10p, minus 9q times 9q. It's a difference of squares. This one is 150 and 216. Let's see. Those have a GCF for sure because they're both even. So let's see. I think I can divide 6 out of both of those. So then I'm left with 25k squared minus 36. Hey, that's good. Those are perfect squares. And if you don't see that you can divide out 6, remember that you can do factoring in stages. So if I just recognize these are both even, I could do 2 times 75k squared minus 108. Now I see that these are not both even, but it might be easier to now tell that they're divisible by 3. A way to know if something's divisible by 3 is to add the digits. So these add up to 12 and these add up to 9. If the sum is divisible by 3, the whole thing is divisible by 3. Anyways, we had 6 times 25k squared minus 36. So that is a difference of squares because 25k squared and 36 are perfect squares. This one, they're both even. They look like they're both divisible by 2 at least. 2. Let's just do 2 and x. So divide out 2x, we're left with 12x squared minus 27. Oh, those are both divisible by 3. So we could change this to 6x, and we get 4x squared minus 9, and there's our difference of squares. So once we've divided out 6x, we're left with 2x times 2x minus 3 times 3. This one we can factor out 5. We're left with 1 minus a squared. This is not well written because we want the a to be first. So what I'm going to do is actually rewrite this at the beginning into standard form and put negative 5a squared plus 5. Then when we factor it out, we're going to take out a GCF of negative 5, and we're left with a squared minus 1. This is actually what we want to have for our difference of squares. Just by convention, we want the variable to be first and the constant to be second. So we have a GCF of negative 5, and then we have a times a minus 1 times 1. This one is a difference of squares. These ones are all trinomials. Well, not all. So the next 8 are all trinomials, so we'll be looking for perfect square trinomials. So we see x times x 3 times 3, and then we ask, is this 2 times x times 3? Yes, it is. So this is a perfect square trinomial. This one is 2y times 2y and 3 times 3. So we say, is this 2 times 2y times 3? Yes. Check. And then it is a perfect square trinomial. This one is 3a times 3a and 2 times 2. So we say, is this 2 times 3a times 2? Question. That's 2, 6, 12. So, yep, that is. So this is a perfect square trinomial. I'm guessing they all are because that's what the paper is, but it's important we talk about the process of checking it. This one is 5m times 5m, 2 times 2. In the middle, we have 2 times 5m times 2. That's 20m, so that's good. That's a perfect square trinomial. 36. There might be more problems I missed. Did I? Oh, I did. I missed a whole column. Oh, well, there's a lot of problems here. I think we're going to use this as the homework as well for today, so I don't want to go through every problem anyways. You did that one? Okay. This one has GCF for sure because everything's got 3's in it. So do we have more than 3? I don't think so. So we have 3 times 12p squared minus 10p plus 9. Well, on this one, interesting. So I took out a GCF, but then I don't have perfect squares anymore. That must mean the middle number is not right. Yeah, let's carry on with that. So 3 times, because we always do GCF first, no matter what. But the fact that you notice I had 2 perfect squares here, 36 and 9. But now that I've taken out the 3, this 12 isn't a perfect square and this 3 isn't a perfect square. So that means we don't have a perfect square trinomial. And if we go back to the original, this was 6p squared and 3 squared. So if we check in the middle, 2 times 6p times 3, that's 36p that should be in the middle. So that's not a perfect square trinomial. That's good that we have an example where it's not. This one, we factor out 2. We're left with x squared minus 4x plus 4. And we do have x times x and 2 times 2. And in the middle, we have 2 times x times 2. Check, that is a perfect square trinomial. I think we've done a lot of these already. And like I said, this is also the homework. So I'm going to go back and just write out the actual answers to a few so we can make sure we understand how to write the pattern. So we'll go back to the first one. Since it's a difference of squares, and this is x squared and 3 squared, we do x plus 3 times x minus 3. On the second one, this was 2y squared and 5 squared, so we do 2y plus 5 times 2y minus 5. So we're just following the pattern from the front page and plugging in our numbers here for A and B in the factored version. And then let's write out a couple of the perfect squares, especially one with a GCF. So let's do this top left one on the screen here. We had x and 3, so that means we have x plus 3 squared. Remember to look at the sign right here between A and B to find the right sign for your trinomial. The second one, we have 2y, and then we have a minus sign, and then the other square root was 3, so we do 2y minus 3 squared. This one down here, the middle left one, remember we cannot write this in factored form beyond just doing a GCF. So we did factor out a GCF. That's somewhat factored, but we don't have one of our special cases for writing linear factors. And then the last one I'm going to write is the next one on that row. So we have 2 is our GCF. And then we have x minus 2 squared was our perfect square trinomial that was left behind after the GCF. So that's how we write those. Just practice and remember to keep looking back at the patterns. You don't really have to memorize these patterns because they're on the star chart. So you don't have to memorize what it says here. What you have to know is how to use it, and when you look at the star chart, what it means. The real trick to today is what's in the homework of when we're presented with a binomial or trinomial, can we recognize that it's a difference of squares or perfect square trinomial? If you don't recognize it, then you can't use the shortcut and it loses all of its value. So always be looking for those two things. They will show up a whole bunch in later math classes as well, so you want to start getting used to recognizing them now.